Hi guys, so we're ready to talk about section 9.2, which is titled rational exponents, right? So a rational number is a number that can be written as a fraction, right? So let's think about what does a fractional exponent do, right? And we're going to see that it's going to be very related to what we talked about last section in terms of different types of roots, right? So the first thing we want to look at is define what's a to the power of 1 divided by n, and then a to the power of m divided by n, right? So you can see that's concept 1. So first, let's tackle the first one, the definition of a to the 1 divided by n. Right? So if we let a be a real number, and let n be an integer such that n is bigger than 1, right? So then if we have the nth root of a, if that is a real number, then a to the 1 divided by n is equal to the nth root of a, right? So if we have 1 divided by a some number, if that's the exponent, then that tells you that's the nth root, right? So let's practice using this definition, right? This idea. So we have a couple of examples. So we're asked to convert each expression to the radical form and then simplify if we can, right? So if we have negative 64 raised to the 1/3 power, right, that's equal to the third root of negative 64, right? So the third root of negative 64 is negative 4, right? Because if I take negative 4 cubed, that's negative 64, right? So the cubed root of negative 64 is negative 4. 16 to the 1/4 is equal to the fourth root of 16, which equals 2. Right? Part C, right, you want to be careful with. Notice in part A, the negative sign is part of the base, right? It's in parentheses. Where in part C, it's not, right? The base here is 36. So this one is actually the same thing as negative 1 times 36 to the 1/2 power, right? So the 1/2 power only goes with the number 36, not the negative sign. If you wanted to include the negative sign, you would want to put that in parentheses, right? Something like that. But that's not what we have, right? So then this becomes negative 1 times, and then to the 1/2 power, that's the square root, right? Index of 2, but we don't typically write that. So we just do the square root, right? So that'd be negative 1 times square root of 36, which is square root of 36 is 6. So this would be negative 1 times 6, which equals negative 6, right? And then part D, that's actually what I had written off to the side, right? The difference between those is C, the negative sign is not included, where D, it is included, right? So this would be equal to the square root of negative 36, which this is not equal to a real number, right? Because we can't take the square root of a negative number, right? If your index is even, the radicand, the part underneath the radical, can't be negative, right? So then the next one, we have 64 raised to the negative 1/3 power, right? So something that you should note is if you have a negative exponent, like if I have x to the negative 2, this equals 1 divided by x squared, right? So essentially, if it has a negative exponent to it, you put it in the bottom, right, if it's in the top of a fraction, right, because we can make it like x to the negative 2 over 1. You put it in the opposite spot, right, and make it positive, essentially, right? So this would equal 1 over 64 to the positive 1/3, right? Because that getting rid of that applying that negative exponent part, we can rewrite it like that. So then this is equal to 1 divided by the cubic root of 64, right? And that's just using the definition that we talked about above, because that's to the 1/3 power, right? So that tells me it's a third root. So the third root of 64 is 4, right? So 4 cubed is 64. So this would be 1 divided by 4, or 1/4, right? Right. So then what we're ready to do now is to define a to the m divided by n, right? So that's going to have a slightly different definition here, right? So the definition of a to the m divided by n, right? So what happens if the your rational exponent, if the numerator is not 1, right, essentially? So the definition is let a be a real number and let m and n be positive integers such that m and n share no common factors and n is greater than 1, right? So if the nth root of a is a real number, then the following is true, right? So if we have a to the m divided by n, that is equal to, so I can think about that as a to the 1 divided by n times m right? So in other words, let me come off to the side and show you what I mean there. So m divided by n, we can think about that as like m over 1 times 1 over n, right? Or essentially m times 1 over n, right? So I can rewrite that with the idea of multiplying fractions, right? And then another thing that we want to review is if I have like a to the x all to the power of y, right? This is equal to a to the xy, right? This is an exponent rule. So if you have a power to a power, you end up multiplying, right? So I'm going to use this idea to rewrite this now. So this would equal a to the 1 divided by n all raised to the mth power, right? Which this, so a to the 1 divided by n from our definition before, this would be equal to the nth root of a all raised to the mth power, right? So that's one definition, right? So another way we can rewrite this is, instead of thinking of this as 1 divided by n times m, we could think about this as the power being m times 1 divided by n, right? That would also be equivalent, right? Multiplication's commutative for 1, but that's just another way we could write that. So we could rewrite this as a to the m all raised to the 1 divided by n power. So the difference here is we would have the nth root of a to the m power, right? So that's like all under the nth root, right? So those are two different ways we can write that, right? And those are equivalent. So example 2, we want to practice that, right? So it's kind of similar to example 1, but now our numerator for our rational exponent is not necessarily 1, right? So this first one, we have 9 raised to the 3/2 power, right? So this is the same thing as 9 raised to the 3rd power, all raised to the 1/2 power, right? Because that's the same thing. I kind of skipped a step, I guess, here, right? This would be the same thing as 9 raised to the 3 times a 1/2 power, right? If you want to write that. So then this would be equal to 9 cubed to the 1/2 power, right? So applying like the power to power exponent rule in reverse, essentially. So then this would be equal to the square root of 9 cubed, right? So 9 cubed turns out to be 729, and we want to take the square root of that, right? So then if you take the square root of 729, you get 27, right? And then the next one, part B, we have 8 raised to the 5/3, right? So this would be equivalent to 8 raised to the 5th times a 3rd power, which would be equal to 8 to the 5th, all raised to the 1/3 power, which is equal to the cubed root of 8 to the 5th. So 8 to the 5th is 32,768, right? So I want to take the cubed root of all of that. And if you take the cubed root of this number, we get 32, right? So I just want to show you real quick, just as practice, pull up my graphing calculator, about how to enter that in the calculator. Right, so the first one, part A, we did the square root of 729, right? So I can just hit second square root and type in 729, right, and hit enter, and we get 27, like we had said, right? So the next one that we want to do is we want to do a cubed root. So actually a cubed root, you can hit math, and then you see the number 4 where it has a cubed root symbol, right? You can do that. So the cubed root, we want to take it of 32,768. Hit enter, and you get 32, right? So then so if you remember example 1 part B, so if you look back to that, so this one, we had the 4th root of 16, right? So I want to just show you how to enter that in too, right? So if you want a root other than 2 or 3, what you do is you hit the root and the index first, and then hit math, and then you want to pick the one with the x, right? So that's option 5, right? It's like a radical sign with an x, and notice it puts the 4 in the index, and we wanted to take that of, I think it was, 16? So type that in, we hit enter, and we get 2 back, right? So so that's how you can use your calculator to find those roots, okay? Right. Right, so the next one, this would be equivalent to 1/27th, right, raised to the power of 4 times a 3rd, right, which would be the same thing as 1/27th raised to the 4th power, all raised to the 1/3 power, right? So the power to power rule. And then a rule, let me come off to the side, a rule that we want to think about here is if I have a fraction like a over b, let's say raised to the nth power, right, this would be equivalent to a to the n divided by b to the n, right? So I think I had shown you that this rule before, right? If you have a fraction raised to some power, then you can take the numerator to that power divided by the denominator to that power, right? So in other words, if I want to simplify this part in the brackets, right, this would be equivalent to 1 to the 4th divided by 27 to the 4th, and all of that raised to the 1/3 power, right? So 1 to the 4th is just 1, and 27 to the 4th is 531,000, 441. Right, so that's all raised to the 1/3 power. So this equals the cubic root, the third root, of 1 divided by 531, comma 441. Right, so just to be clear, that's not a 9, that's a 4. 4, 1. Right, so then it's a fact, like, so if I have, let's say, the nth root of a fraction like a over b, then this is the same thing as the nth root of the denominator divided by the nth root of the denominator, right? So that holds true, right? And really, what you're doing is kind of like applying this this rule, right? So this would be the same thing as the cubic root of 1 divided by the cubic root of 531,000 number here. Right. So in the cubic root of 1, we know is 1, right? So then the cubic root of 531,441 turns out to be 81, right? So you could type that in your calculator and double check. So the answer we get is 1 divided by 81, right? So I guess alternatively, if you didn't want to go from here to here, like do this step, what you could have done is from here, you could have applied this to be 1 over 1/3 divided by 531, comma 441 raised to the 1/3 power. So just using this exponent rule here, and then you could convert that then to be the cubic root of 1 over the cubic root of 531, 441, right? But then we would get to the same answer, right? So the only thing is if you didn't remember or know this connection, right? But you should definitely know that, right? If you don't know it, something you should know, right? All right, so the next one, we have 32 raised to the negative 4/5 power, right? So remember, with a negative exponent, this makes this 1 divided by 32 to the 4/5. Oops, I don't want that to look like a 9. Right, so this would be equivalent to 1 divided by 32 to the 4th, all divided by, or excuse me, not divided by, but the 5th root. So in other words, 1 divided by the 5th root of 32 raised to the 4th power, right? So this would equal 1 divided by the 5th root of, so 32 to the 4th power is a pretty big number. It's 1,048,576, right? And then when you take the 5th root of that ends up being just 16, right? So again, if you want just real quick practice with this, right, if I want to put this in my calculator, I would hit 5 because I want the 5th root, and then hit math, and then option 5, right, the one with the x, and then I would just type in my value, 1,048,576, hit enter, and we get 16, right? So that's how you can easily do that in your calculator, right? So the next one, part E, we have negative 4 raised to the 3/2 power, right? So this is the same thing as negative 4 cubed, and then the square root of that, right? Again, it's just using that definition we talked about earlier above, right? So this would equal, so negative 4 to the 3rd power is negative 64. So we'd have the square root of negative 64. But again, I can't have a negative value underneath an even root, right? Because that's like a 2 here, a square root. So this would not be a real number. So we can't simplify this, right? So then the next concept 2, is looking at converting between rational exponents and radical notation. So example 3, we want to convert each expression to radical notation and assume all variables represent positive real numbers, right? So t to the 4/5, right? That would be equal to t to the 4th times 1/5, right? Which equals t to the 4th all raised to the 1/5, which equals the 5th root of t to the 4th. Right? So this next one, this guy, this is the same thing as 2 to the 1/4 times y to the 1/4 times 3, right? Which equals the 4th root of 2 times the 4th root of y cubed, right? So I guess think about it like this order, 3 times 1/4, right? So in other words, it's like y cubed to the 1/4 power, right? If you're having trouble jumping from that. So then something else that you should know, just to refresh, is if you have like the nth root of a times the nth root of b, that's equal to the nth root of a times b, right? So if you have the same root, then you can combine it in one root by multiplying the two radicands, right? So here, this becomes the 4th root of 2y cubed. Right? Part C, we have 10 times p to the 1/2, right? So again, it's important to recognize that this is 10 times p to the 1/2. This exponent only goes with p, right? If I wanted the whole thing raised to a half, you'd have to put parentheses around it, right? These are different things. These aren't equal, right? Those are different, totally different things, right? So this would just be 10 times the square root of p, right? That's the 1/2 power. Or we could just write that as 10 square root of p, right? It's understood that that's multiplication in between those. Right? So similarly here, part D, this would be equal to 11 times q to the negative 2/3, right? So first I would apply the negative exponent, so that would be 11 times 1 divided by q to the 2/3, right? Which equals 11 times 1 divided by q times 2 times the 1/3, right? So one thing I can do is I can go ahead and, if I put 11 over 1, we can just multiply these fractions right over top, right? So this would just be 11 divided by, and then this would be q squared to the 1/3 power, right? We could rewrite it that way. Then this would be 11 divided by the cubic root of q squared. Right, so that's the answer that we want to get to. Right? So now example 4 is we want to convert to an equivalent expression using rational exponents, right? So in other words, going backwards, right? So before we're starting out with the rational exponents and trying to go to the radicals, but now we're going the opposite. Right? And again, it's just to get practice with the notation. So the cubic root of x squared, that would be the same thing as x squared all raised to the 1/3 power, right? So a power to a power we can multiply. So this would be x raised to the, oops, hang on, sorry about that. Right, this would be equal to x squared raised to the 1/3 power, which is the same thing as x raised to the 2 times a 3rd power, right? The power to a power rule whenever we multiply. So then this just becomes x to the 2/3, right? 2 times a 3rd is 2/3. Right, so then for part B, this would be equal to 5 y all in parentheses to the 1/2 power, right? And notice I put parentheses around it because the whole thing is underneath the square root symbol, right? So if I had just written 5y to the 1/2, right, this would equal 5 times the square root of y, right? So those are different things, right? So be careful of that. So if you want the whole thing underneath the square root or the radicand, right, you need to put that in parentheses. And then part C, we have 5 times the square root of y, right? So this would be equal to 5 times y to the 1/2 power, right? So I guess I just had done that, right? Just to show you the difference. Right, so then the next concept is properties of rational exponents, right? So what we have here is just a reminder of the exponent rules. I just took this out of the textbook, right? It says let a and b be non-zero real numbers, let m and n be rational numbers such that a to the m, a to the n, and b to the m are real numbers, right? So if you're multiplying like bases, right? So here's like the property we're going to add, right? And you should probably already know that, right? From, we worked with polynomials and multiplying polynomials and things. That's something that you would have had to need for that, right? But it still applies for rational exponents, right? And then dividing like bases, right? We subtract, right? And so forth. The power rule, product rule, quotient rule. So all these rules that you've seen before, really it's just shown here just to reiterate that we can do this with rational exponents as well, right? They don't have to be whole number exponents or integers like maybe you've done before, right? So let's just practice these properties. So number 5, part A, we have x to the 1/2 power times x to the 3/4. Right, so that's the same base multiplied, right? So we end up applying the rule where we add the exponents, right? So this would be x to the 1/2 plus 3/4, right? So in order to add those, we need to get common denominators. So 1/2 can be written as 2/4, right? So then 2/4 plus 3/4 is x to the 5/4, right? So that's simplified. Right, so the next one, first thing I would probably do is you could actually rewrite this as 4 times k to the negative 2/3 over k to the 1/3, right? So I think maybe that might be helpful to work through this so we can simplify this part, right? So I'm just pulling this 4 out, right, making the factor be out in front instead of in the numerator, right? But those are equivalent, right? If I put this over 1 and multiply straight across, then I would get back to what I started with, right? So that works out. So then when I have like bases and I'm dividing, right, we end up subtracting the numerator. So this would be 4 times k to the negative 2/3 minus 1/3. So negative 2/3 minus 1/3 is negative 3/3, right, which is negative 1. So this would be equals 4 times k to the negative first power, right? And negative 1, negative 1 power puts that in the bottom, right? So this would be the same thing as 4 times 1 over k, right? Just applying the negative exponent, which this would just be the same thing as 4 divided by k, right? So that's really the most simplified we can get there, right? So the next one's maybe a little crazier. Right, so we have a fraction, kind of big picture. I have a fraction raised to the 6th power, right? So that's the very first thing I would tackle is just putting the numerator to the 6th power divided by c to the 5/8, the denominator, raised to the 6th power, right? So to me, I'm just thinking this as a big fraction raised to the power of n, so that's a to the n over b to the n, right? I'm thinking about this rule, right? So now I have two factors in raised to the 6th power, right? So to me, that's like this rule. If I have a times b raised to the n, that's equal to a to the n times b to the n, right? I have to take each factor raised to the exponent, right? So this would be a to the 1/3 power raised to the 6th power, and then times b to the 1/2 raised to the 6th power, all over c, and this would be 6 times 5/8, right? We multiply. So this would be a to the 1/3 times 6, b to the 1/2 times 6, and then c 5/8 times 6. Right? We're just trying to simplify those. So this would be a to the 6/3, right, times b to the 6/2, all over c to the 38. Right, and then we can simplify each of these. So 6 divided by 3 is just 2. 6 divided by 2 is 3, right? So we get a squared times b cubed in the top. And then for this fraction, for the c, or the base c, we can divide top and bottom by 2. So that becomes c raised to the 15/4 power, right? So that's as simplified as we can get there, right? Just applying those rules, right? So then the very last thing we want to do in concept 4 is just look at an application, using rational exponents, right? So here's an application. We're told the formula for radius of a sphere is r equals 3 times the volume divided by 4 pi, all raised to the 1/3 power, right, where v is the volume. We want to find the radius of a sphere whose volume is 113 4/100 cubic inches. Use 3.14 for pi, right? So my volume is 113.04 cubic inches. We want to use pi, an approximation for pi, as just 3.14. We want to use this. So if I just plug these values in, I'd have r equals 3 times v divided by 4 pi, all raised to the 1/3 power, right? So that's just my equation. So then if I plug the volume in, that would be 3 times 113.04, and then divided by 4 times 3.14, right? So just plugging in the values for v and pi that we want to use, all raised to the 1/3 power. So this would be the same thing as the cubic root of 3 times 113.04 divided by 4 times 3.14, right? So if I simplify the inside, the radicand, this ends up becoming the cubic root of 27, which is equal to 3, right? So the radius is equal to 3 inches. All right, so that's all I have for this section. So if you have questions, make sure you're contacting me. Let me know. Thanks.